In this series of lectures, we'll introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear but might not be mathematically rigorous. In particular, we'll not use the famous epsilon delta language. In this video, we'll discuss how to derive derivatives of the exponential function e to the x and the trigonometric function sine x. First, let's look at e to the x. Let's recall what is the number e. This number is called the Euler number and is also the base of the natural logarithm. Now, e by definition is given by the limit of the sequence, as we said in a previous lecture, 1 plus 1 over n to the power n. This limit gives a number which is irrational. In terms of decimal digits, that means the decimal digits, there are infinitely many decimal digits, they are not repeating. Okay, so that's how we define the Euler's number. Now, the important thing is, if you look at the exponential function when the base is e, then for this exponential function, the derivative of the function is itself. Sometimes people use this way to define the Euler number e. That means Euler number means the number that the derivative of the power function of this exponential function is itself. All right, but here we start from this definition, the limit of the sequence, and we're going to show that the derivative of the function e to the x is itself. Okay, let's prove that. Okay, so what we'll do is we'll use definition. By definition, right? By definition, analytically, the derivative of e to the x, this is another way to represent the derivative df over dx. This is the way we often use. We use f prime. Okay, so that's the common way we'll use in this series of lectures. Okay, anyway, by definition of derivatives, e to the x, which is given by the limit. So h goes to 0, h, and it's e, x plus h, and minus x, right? Okay, so here x is fixed. X is fixed. And h is changing and it's approaching to 0. Okay, all right, so this is just by definition. And here let's do some algebra because there's ex and ex, right? You see ex to the power h because it's the power. This is just e to the x times e to the h, right? Okay, so let's put it here. So this is the limit h to 0, and this is h and ex times e to the h minus ex. Okay, so we have a common factor e and ex, and we can put to the this to the front. Okay, so we can pull it out, right? So we can pull this ex out, and what the left times is the limit h goes to 0 and h and eh minus 1, right? Eh minus 1. Now we want to show that whether this is equivalent. This is equivalent to the e to the x, right? E to the x, and then you see. It just remains to show that in order to establish this, we just need to show that whether this one actually equivalent to 1. So this is our next step, right? After we establish this, then we are done. Okay, all right. Okay, so then to continue, as we said, all we need to show is this one equals to 1, right? After this one is verified, then we conclude the derivation. If you look at this more carefully, you say, okay, e to the h. Now, what is this one? This is just e to the 0. In fact, this is just the derivative of the exponential function evaluated 0. But anyway, so let's prove this. Okay, let's establish this one. Okay, so now let's recall that e is equals to the limit, right? So this is just how we define, how we start from. So the limit of the sequence, 1 plus n to the power n. Now, you can show by yourself this is also equal to, here the n is natural numbers, so positive integers. Now you can replace, so we start from n, this is positive integers, right? Positive integers. Now we can actually replace this n by any positive number, let's say lambda, right? So lambda goes to infinity, positive infinity, and 1 plus 1 over lambda and to the lambda. So lambda is just real numbers. Right, positive real numbers. Right, you can go from the positive integer to positive real numbers. This I just leave as an exercise. You can do, you can try by yourself. But anyway, intuitively, it's not so hard to see, right? Okay, and then from here, if you let lambda, so I fix the number h, because it's very close to 0, we say it's just less than 1, right? Now, if I choose lambda to be n over h, right? So it's okay, just n over h, right? N is part of integer. And then from here, we get the first one, step 1, we'll get, if I use lambda to this and I plug into here, I will just get an expression of e to the h. So this guy will just be the limit. As n goes to infinity, 1 plus h over n to the power n. Okay, so this is first thing we established. All right, so this is what we want. Okay, now I claim this. Now I claim step 2. I claim this 1 plus h over n to the n, right? So this one, this is bigger than 1 plus h, but it's less than 1 plus h squared and plus h to the n. Now, why is that? Okay, why is that? Well, we can just use the binomial formula. In fact, 1 plus h to the power n, right, to the power n. If I use the binomial formula right out, so this is k from 0 to the n choose k, and h to the n and to the power k, right, to the power k. Okay, if you write this one out, you find this is just the first one will be 1, the next one will be h, and then whatever remains, you say, okay, is n squared, and this is the n choose 2, and this is h squared, and right? And the last one was n to the n, and 1, and h to the n. Okay, now each coefficient, if you look at each coefficient, which is just the n to the power n to the k, right? And this is n choose k. You can very easy to see this is less than 1, right? Okay, so this is less than 1. This is less than 1. Then you just get those things. It's less than this, right? It's less than this. Now we can calculate this one out. So this is just 1 minus h to the n plus 1 and 1 minus h, right? 1 minus h. Okay, we verify that. Now let's see. Okay, after we verify this, we can derive. So I'm going to erase that. Right? I'm going to erase this part. Okay, and we have, so from the step 2, right? We have this 1 plus h over n to the n. This is bigger than 1 plus h, and is less than 1 minus h, and 1 minus h n plus 1. Now, the e is the limit, right? So e is the limit, you see, it's the limit of this. So if I let n goes to infinity, this n goes to infinity, right? N goes to infinity. Then you see this term, because h is between 0 and 1, and we said it before, if h is between 0 and 1, if you take the power, this will go to 0 as n, as the power n goes to plus infinity, right? Goes to plus infinity. Okay, so from here we conclude what? We conclude this one will just go to 1 over 1 minus h. Okay, so I get the EH is bigger than 1 plus h, but it's less than 1 over 1 minus h. Okay, so that's equality what I get, right? That's equality what I get. Okay, now let me erase. Okay, so that's all I need. Okay? I'm almost done. Okay, that's all I need. And then we'll have the EH, right? Okay, so for here, I just fix H is it will be 0, 1, right? Of course, there's another direction, but let's just do this, okay? And then the EH minus 1 over H, this will be bigger than 1, because if you put 1 over H here, and then if you put this one, if you put this part, right? If you put this part here, you see, okay, it will be less than, you see, okay, this guy will be less than, this one will be less than 1 over 1 minus h, right? 1 minus 1 over h, because 1 over 1 minus h minus 1. This will just be h over 1 minus h, and divided by h to cancel with each other, right? You cancel with each other. If you plug this back here, if you replace this by that, by simple algebra, you'll find this is it's 1 over 1 minus h. Okay, now, and then you say, okay, if I send the h goes to 0, if I send h to 0, this one will just be 1. It doesn't matter. And this one on the right-hand side, when h goes 0, we just replace this by 0, it's 1. So from the right-hand side and left-hand side, it will force the whole thing. The limit is 1. Okay, so this is how we use this expression of e to the h, and how we use the binomial formula to get a bound of this expression, and we get this inequality, and eventually we just get this limit. Okay, all right. Okay, now so we have derived, we derive this limit of this one is 1, and therefore this is just the derivative of ex, it's just itself. Okay. All right, now let's look at the derivative of sine x. The conclusion is the derivative of sine x we write as dx, or we write as sine prime x equals cosine x. Okay, let's verify this. All right, let's verify this. We just do by definition, right? We say, okay, by definition, the derivative of sine x, right? So this is pure definition. It's the limit as h equals to 0, right? So this is h, this is sine x plus h, and a minus sine x. This is definition, right? Nothing else. It's just definition. Okay. Then the question is, we say, okay, but then how you simplify this, right? When you look at this sine x something minus something, so okay, we have a trigonometric identity, right? Let's recall the trigonometric identity. You know, sine a, let's say maybe sine alpha minus sine beta. We have formulas twice of sine alpha minus beta over 2 and cosine alpha beta over 2. I have this formula. Okay, let's apply the formula here. Okay, that's what we want to get. So just the limit as h equals 0, and this is the h, right? So this is h, it's twice, and sine, right? So sine, this will be h over 2, and a cosine, this is the x plus h over 2, right? H equals 2. Okay, now we can separate this into two parts, right? So let's separate this into two parts. One part is this, right? And the other part is that, okay? All right, so we have, so all right, let's say this is the limit as h equals 0. So this is h 2 sine h over 2, and the limit as h equals 0 and cosine x plus h over 2. Now this one is it's simple. You say when h goes 0, the cosine is continuous, so this one just goes 0. So it's okay. So this guy just cosine x, right? Simple. Now the more tricky part is this one. What is the limit of this? Okay, let me rewrite this, and then you see this is something we saw before. Okay, let's write. It's if I write this, just it's this equals. Hold on. So this equals the limit as h equals 0, right? Sine h over 2 and h over 2. I just pull this 2 here. And if I write, you say, okay, if I write this guy as just another number, let's say it's theta, whatever. So this one is, I put is theta. And then, okay, so this is cosine x. I copy down here, right? It's cosine x, copy down here. Now, and then you see, we say, okay, what is this one? This one is just equals the limit. Theta goes 0, but theta just h over 2. So theta goes to 0. And this is sine theta over theta and times cosine x. Now, what is the limit? Sine theta over theta. Remember, so this is what we derived in a previous video. The limit of this one is 1 by a geometric approach. So this is, we established before, the limit of this one equals 1. So this is what we need in order to establish the derivative of sine x is cosine x. So you basically use two things. One is the trigonometric identity. So this tells us how we go from the difference to product. And then we need to use the thing that we proved before, right? So this limit, and combine this two things together, we derive the sine limit equals cosine x.